In the previous video, we worked on a consumer's choice model with the Cobb-Douglas utility function to find the optimal consumption bundle for the consumer when they're limited to a budget of Y and face prices of P1 and P2. In this video, we want to reflect on the solution process and think harder about the solutions we obtained in order to gain some more intuition from the process. To find the optimal consumption bundle, we first wrote down the utility maximization problem with the objective function and the constraint. From there, we wrote down the Lagrangian, and then we took first-order derivatives with respect to the control variables, Q1, Q2, and the Lagrangian multiplier lambda. And then we forced these first derivatives to be 0 and obtained our first-order conditions. These gave us three equations of three unknowns that we're able to solve. By combining the two first-order conditions, we reach our tangent condition of marginal rate of substitution equal to marginal rate of transformation. And then we use this expression in conjunction with our budget constraint, equation 3, to solve for the optimal consumption bundle of Q1 star and Q2 star. The first place I would like to reflect on is the role the budget constraint plays in locating the optimal consumption bundle. In particular, I'd like to bring your attention to the step in our solution where we combine expressions 4 and 3 together to find the solution. If you pay closer attention to expression 4 alone, you realize that it is entirely derived from the tangent condition and the tangent condition alone. We have emphasized the tangent condition so much in our graphical solution that it seemed like the only key we need to find the optimal solution is the tangent condition. But that's actually not the case. Let's look at this expression 4 here. It says that according to the tangent condition, Q2 is in fact a function of Q1. In other words, for every Q1 you can imagine, equation 4 will tell us a corresponding Q2 that satisfies the tangent condition. In fact, it is a straight upward sloping curve here, given alpha and the prices. In other words, it is not giving us the optimal consumption bundle at all, which we know should be that unique point that is tangent to the indifference curve on the budget constraint. Did you realize what's missing here from the tangent condition to the optimal consumption bundle? Well, what's missing is the budget constraint itself. If you remember, the first part of our graphical solution was an entire argument about how the optimal consumption bundle must lie on the budget constraint itself. So tangent condition is not the only condition we need to find the optimal solution. See, that equation 4 tells us that there are many Q1 and Q2 combinations that satisfies the tangent condition, but not all of them are on the budget constraint. In fact, there is only one such point that is on the budget constraint. This is why we found a unique pair of Qs as the optimal solution when we combine the tangent condition 4 with the budget constraint equation 3. We need both of them, and the Lagrangian approach automatically involves both of them for us. Graphically, this is how the intuition goes. The tangent condition says that the slope of the indifference curve needs to be equal to the slope of the budget constraint. But it didn't say which indifference curve it is. And in addition, if you look at the tangent condition itself, in particular the right-hand side, it only uses the slope of the budget constraint, which is P1 over P2, but not the budget itself. So it actually doesn't even say we need to be on the budget constraint itself at all. Recall that the budget tells us about the intercepts of the budget constraint. If you remember from the previous video on the budget constraint, we found the intercepts of the budget constraint by spending all of the budget on good 1 or good 2, which are y over P2 for the Q2 intercept and y over P1 for the Q1 intercept. Without specifying the budget y, we can find many lines that have the slope specified by the right-hand side of the tangent condition. As long as it has this particular slope of minus P1 over P2, so that it is parallel to the real budget constraint we have. We can see that on the graph, I can try to draw many lines that shares the same slope as the budget constraint, such as this one, or this one, or this one, or this one, or this one. You can see that it is all too easy to find these parallel lines that shares the same slope as the budget constraint. And they're all tangent to summing difference curve. In fact, if we repeat the process of drawing such lines parallel to the budget constraint and finding the point that is tangent to any indifference curve, we will be able to find an entire track of such points. However, only one such point lies on the budget constraint. And that point is the one that maximizes utility, which is the tangent point on the budget constraint. If we go back to equation 4, in fact, equation 4 is precisely the expression that describes this track of tangent points between any parallel curve to the budget constraint to some indifference curve. And with Cobb-Douglas utility function, that curve is a line that has a positive slope. All the points along that curve will satisfy the tangent condition. And this is why we need to use the equation 4 together with the equation 3, which is our budget constraint, to find the unique combination of Q1, Q2 that satisfies the tangent condition and the budget constraint simultaneously. This observation is generally true regardless of the choice of the utility function. I would like to note that a specific procedure we focus on here applies to optimization problems with one constraint that holds inequality. The solutions to problems with more constraints and sometimes inequality constraints are generalizations to the procedure that we use here, but they share a very similar flavor. For our purposes, the single equality constraint scenario is sufficient, and we will be using it throughout the course in several different models. It is therefore essential that you get familiarized with solving Lagrangian. I'm sure that with time and practice, you'll get the hang of it very soon. You might wonder, why bother using Lagrangian, given that we know the solutions are just given by the tangent condition and the budget constraint? There are a few advantages to the Lagrangian approach that makes it our go-to approach to solve constrained optimization problems. First, it is relatively easy to remember. You just need to write down the optimal program relatively intuitively with the objective function and the constraint. And then the Lagrangian just follows from it. You can then just do the recipe with first-order conditions and solve, and voila! We have the solution. On the contrary, if you choose to go directly for the tangent condition, you will have to rely on memorizations of marginal rate of substitution, marginal rate of transformation, the order of the goods, which are all very easy to get wrong. Secondly, the Lagrangian approach may appear cumbersome at first, but it actually adds no extra algebra. When taking the derivatives for first-order conditions, you're essentially calculating MRS, MRT anyway, which you would need to do, regardless of which way you approach the problem. And then solving it with the budget constraint is also required, even if you just go with a graphically derived solution. So the burden of algebra is actually the same, but the process is broken down intuitively in the Lagrangian approach, so it should take relatively less mental energy, once you're familiar with the recipe, that is. Finally, and perhaps most importantly, it is generalizable to more complicated problems. One example is if the consumer chooses more than two goods. Then the graphical solution is very hard to think about. But the Lagrangian approach will lead us to the answer without adding much complexity at all. And it will reveal to us what the intuition can generalize. Later on in this course, you will see that we will use the Lagrangian on very different looking problems, whereas the intuition of MRS equal to MRT just doesn't translate that easily. Some of you might remember that at the introduction of the Lagrangian approach, I said that the method works when the objective function behaves nicely. So what does that mean exactly? When can you trust it? Well, the answer is a little technical, so we won't get into it too much. For now, we just need to know that many economists have investigated this when they chose utility functions. Most of the utility functions we work with are nicely shaped so that this approach will lead us to the optimal solution. This includes the Cobb-Douglas utility function and the CES utility functions. There are a few exceptions that we'll discuss later on. The optimal consumption quantities tell us, under given prices of each good and a given budget, how much of each good the consumer should purchase in order to maximize their utility. Now we have figured out these optimal quantities. We can ask one additional question. What is the level of utility the consumers would have when they choose this optimal consumption bundle? In other words, what is the highest possible altitude that the consumer will be able to reach on the utility hill when they face a budget of Y and prices of P1 and P2? In such a decision environment, what is the best possible utility level they can get? Well, now, finding the answer to this question is relatively easy now, because we already figured out that consuming Q1 star and Q2 star are the utility maximizing choices given these prices P1, P2, and a budget level of Y. So what we need to do is just plugging in these quantities into the utility function and find the corresponding utility level given these exogenous variables. In other words, we just need to figure out the corresponding altitude on the utility hill when we choose the Q1, Q2 coordinates at the tangent point along the budget constraint. The algebra is even simpler than this idea. If we plug in the soft Q1 star and Q2 star into the positions of Q1 and Q2 in the Cobb-Douglas utility function, what we would have is that we're going to raise Q1 star by the power of alpha and raise Q2 star by the power of 1 minus alpha. And then because in each term you would have y being raised to the power of alpha and y being raised to the power of 1 minus alpha, we can pull the y terms out and collect them. Their powers add up to 1, so then that will give us this particular expression. Now we obtained a level of utility expressed entirely by the exogenous variables of P1, P2, Y, and alpha. This expression has a very particular meaning. It says that given that this consumer's preferences are described by a parameter of alpha, and if you tell me that the prices a consumer faces for the two goods are P1 and P2, and the budget is Y, then this function will immediately tell me what the level of utility the consumer is able to get when they make the best possible choices. The magical part is that all the optimal choices in quantities are already wrapped into this function, and they all happen implicitly by itself now. To see this point, let's say that the consumer budget doubles from $100 to $200. And we might wonder how the consumer's utility would change as a result of the doubling in income from 100 to 200. Well, as the budget changes, the consumer would choose different quantities to consume. And when they choose a different optimal consumption bundle, their utilities will probably change. So it is actually quite a lot to keep track of. But hey, as long as you have this particular expression here, you'll be able to see immediately that if we double y, all of these terms in the parentheses will not change at all as long as alpha does not change and the prices don't change. So doubling the budget y will exactly double the utility the consumer is able to get. And this relationship is not even limited to the change from 100 to 200. It holds true if you double it from 1,000 to 2,000, 10,000 to 20,000, etc., etc. And that's the power of this particular function. We saw that from the example. With this function, you don't actually need to resolve the utility maximization problem to answer this question. If the change in the consumer's utility is all you care about, you don't even need to figure out how their consumption bundle will change. This function provides you with a mapping from the consumer's decision environment straight to the outcome of the optimization problem. This function turns out to be very useful in various types of analysis because it is also a utility function, but a function of the decision environment instead of the quantities of goods. We call it the indirect utility function. By contrast, the utility function that we've grown familiar with is called the direct utility function that maps directly from quantities that the consumer enjoys into the utility for the consumers themselves. An important difference between these two types of utility functions is that a direct utility function need not be optimized at all, whereas the indirect utility function already embeds all the optimal quantity choices. For every utility maximization problem with a direct utility function, you can always derive the corresponding indirect utility function after obtaining the optimal consumption choices. And then just plug in the Q1 star, Q2 star back into the utility function, and then you'll be able to obtain the indirect utility function. We'll see the indirect utility function reappear again and again throughout this course. To wrap up the utility maximization problem of the Cobb-Douglas utility function, I would like to summarize the properties of its derived demand functions. These demand functions are relatively simple, so they're actually very easy to work with. In addition, they have some intuitive and impeding properties. Each demand is increasing in the budget or income. As Y increases, the quantities demanded will increase for both Q1 and Q2. In addition, these demands are decreasing in their own prices. When P1 increases, Q1 becomes smaller. When P2 increases, Q2 becomes smaller. We can verify that by taking derivative of Q1 star with respect to P1 and taking derivative of Q2 star with respect to P2. You can verify that these derivatives all satisfy the desirable properties with the signs that we expect to have. These are desirable properties that match reality pretty well. However, it is somewhat too simple in a sense that the demand for each good does not respond to the price of the other good at all. If we take derivative of Q1 star with respect to P2, we will find that derivative is actually zero, and vice versa. This is not a very intuitive property. When apples becomes more expensive, we would expect the consumer to respond in their consumption of bananas in one way or another. Maybe they shift their consumption towards buying more bananas, or maybe because apples got so expensive, the consumers now feel like their wallet is being pinched a little, so they're buying less fruits altogether. But it is unlikely that the demand of one good is not affected by the price of another good at all. This property is in fact implied by the feature that an expenditure on each good is a fixed proportion of the budget, and that proportion is entirely determined by the preference parameter alpha. In other words, changes to the price of good 2 does not lead to adjustment of expenditure on good 1 at all. As long as the price of good 1 itself does not change, the demand for good 1 remains the same. We will discuss some more intuition about this property in the next section, but overall, this property makes the derived demand from the Cobb-Douglas utility function undesirable for many applications, where we expect the demand to respond to prices of other goods. So now let's turn to another example where we solve the consumer's utility maximization problem with a more sophisticated utility function, the CES function. Although this is a different looking utility function, we're going to see that the same process in the Lagrangian approach will lead us to the solution. We will see that the algebra only changes very slightly, and this utility function will derive demand functions that are widely used in many economics models. Now let's try to solve it. First, we will write down the constraint optimization problem. Remember, we need to clearly specify the four essential elements: the maximization operator, the objective function, the control variables Q1 and Q2, and the constraint, which is just expenditure is equal to budget. That does not change at all when we switch from one utility function to another. Now with the programming in place, we can write down the Lagrangian, L, which again is just the objective function plus lambda times the modified version of the budget constraint, where we clear out the expenditure to the other side and be subtracted by the budget y. Now with the Lagrangian, we can take derivatives of the Lagrangian with respect to each control variable Q1, Q2, and lambda. And then we're going to set all of them to 0. That will give us 3 first-order conditions. Could you pause the video here and give it a try? Please take a few minutes to do that. This is an important exercise. All right. If you actually take the time to try it, and I highly recommend you do that, you would find, hopefully, very similar expressions as what I have here. The first two first-order conditions, again, are just marginal utility with respect to good 1 and good 2 minus lambda times the price of that good, P1 and P2. And the third first-order condition is, again, just the budget constraint. And again, we will use the same trick to try to combine the first two first-order conditions into the same equation. To do that, we will move the negative terms to the other side, and then we'll be able to divide the left-hand side by the left-hand side, because again, equation 2 is holding true when the second first-order condition is satisfied at Q1 star and Q2 star. And again, this leads us to the tangent condition. And in fact, the marginal rate of substitution isn't too terrible at all, although the marginal derivatives aren't too pretty. And the reason is, as we have illustrated when we calculate the marginal rate of substitution for the CES utility function, this term is common to both derivatives. So they're just going to drop out when we divide one equation by the other. And that gives us this not too bad looking tangent condition. Notice that this equation only contains Q1 and Q2, but not lambda, just like our budget constraint here. So what we can do is we can try to rewrite one of the quantities in terms of the other, and then substitute into equation 3 to solve for the unknowns, which are Q1 and Q2. Now, to do that, let's try to write Q2 in terms of Q1 here, and the exogenous variables, of course. So first, we need to get rid of this power on Q2. At this point, it is perhaps useful to remind you of some algebraic rules on power operation. Let's say that we have a function that's x squared is equal to some constant a, where x is the unknown, and the right-hand side of the equation a is greater than 0. Then this function is in fact equivalent to x is equal to the square root of a, which we know is just x equal to a to the power of 1/2. These expressions are entirely equivalent. Well, what if we have an equation that is x to the power of 3 is equal to some constant a? Well, again, this is equivalent to x is equal to a raised to the power of 1/3. You see that the generalized rule is that we take the power on the unknown and then we just raise it to the other side of the equation by its reciprocal. So a power of 2 becomes a power of 1/2, a power of 3 becomes a power of 1/3. This rule doesn't limit to the powers that are integers. If we have a square root of x that is equal to a constant a, this equation is equivalent to x to the power of 1/2 is equal to a, and we know that this equation is equivalent to x to the power of a squared. Similarly, if we have x to the power of 1/3 is equal to a, then we know it is equivalent to x is equal to a to the power of 3, and so on and so forth. What we're doing is simply taking the power on x and then raise it to the other side of the equation by its reciprocal. And these equations are all equivalent. So now let's say we have an equation that says x raised to the power of 1 minus rho is equal to some constant a. How can we get rid of the power on x and still have an equivalent equation? Well, what we can have is x is equal to a to the power of, you guessed it, 1 over 1 minus rho. That's exactly the same rule. Now, on the right-hand side of our slides here, what we can do is we can treat this entire ratio of Q2 over Q1 as x and treat this ratio of P1 over P2 as a, which is a positive constant. So now we're able to rewrite our expression, which is Q2 over Q1 to the power of 1 minus rho is equal to P1 over P2 as Q2 over Q1 is equal to P1 over P2 raised to the power of 1 over 1 minus rho. And voila, that's exactly the expression we have after we multiply Q1 here on both sides of the equation. So there we go. That gives us equation 4 here on the slide. So from here, we can proceed and solve the problem by directly plugging 4 into 3 and solve for Q1 star. But after repeated work on this function, economists realize that the job can be simplified if we wrap this power of 1 over 1 minus rho into one entire package. And we're going to call this package sigma. In fact, we're going to throw on a negative sign as well to this package. So instead of writing this package as sigma, we're going to write it as minus sigma. The basic idea is that in later algebra, we will only work with this package of 1 over 1 minus rho as a whole, as opposed to its separate pieces, the ones, the rows, etc., etc. So packing it up like this will simplify the upcoming algebra and also make the results a little bit prettier, so we can interpret it better. Adding the negative sign just makes the powers look slightly better in some circumstances, but it's really a personal choice. But for here, we're going to stick with this expression. Now we'll take advantage of this trick and rewrite 4 into 4 prime. Notice that, again, the only thing that we have changed from equation 4 to equation 4 prime is just to wrap up this power of 1 over 1 minus rho into minus sigma. So now we can plug 4 prime, which is an expression of Q2, into equation 3 here, into the position of Q2 here. And if we plug in that expression, this is what you see. This expression is exactly what we have just obtained in 4 prime. which is the expression for Q2 in terms of Q1 and the prices. So now what we can do is we can distribute the power of minus sigma onto P1 and P2 respectively. To see that, we can write down the budget constraint, y minus P1 Q1 minus P2 times the expression for Q2 in equation 4 prime, which is P1 over P2 to the power of minus sigma times Q1 equal to 0, which is our equation 4 here. And now, distributing the power of minus sigma into the term of P1 over P2, we have y minus P1 Q1 minus P2 times P1 to the power of minus sigma and P2 to the power of minus sigma times Q1 is equal to 0. And now what we can do is we see a P2 here and a P2 to the power of minus sigma on the denominator. So we're able to combine these two terms, and our equation becomes y minus P1 Q1 minus P2 times P2 to the power of sigma, because we're flipping the P2 to the power of minus sigma from the denominator to the numerator. That takes out of the negative sign the power, times P1 to the power of minus sigma times Q1 is equal to 0. And now we're able to combine the power on these two P2 terms, and that gives us y minus P1 Q1 minus P2 to the power of 1 plus sigma times P1 to the power of minus sigma times Q1 is equal to 0. Now notice that in the second and third term, we have a linear term of Q1, which we can factor out. And these are the only places we have the unknown of Q1. So after factoring it out, we have this expression on the slide where the product on Q1 in the second term is just P1, and the product on Q1 in the third term is P2 to the power of 1 plus sigma times P1 to the power of minus sigma. So after pulling Q1 out, we have this expression. And then to solve for Q1, we just move this expression to the right-hand side of the equality and then divide both sides by this term in the parentheses. That gives us a solution of Q1 in terms of P1, P2, y, and sigma, which are all exogenous variables, which is our solution of Q1 star. Recall that sigma is, by our definition, just another way to express the exogenous parameter of rho in the utility function. Well, this could be the end for the solution of Q1 star, but what economists usually do is that we usually try to rewrite the expression slightly by multiplying this term in the bracket here by P1 to the power of sigma divided by P1 to the power of sigma, which has a value of 1. Because we're multiplying this entire expression by 1, we're not really making substantive changes to the equation at all. However, when we multiply this term through, what happens is on the denominator, P1 to the power of sigma will cancel out with this P1 to the power of minus sigma. And it will combine with this term of P1 to the power of 1. So on the bottom, when we multiply P1 to the power of sigma with the denominator, we have P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma. And this looks much symmetrical. On the top, we'll just have this term of P1 to the power of sigma as opposed to 1. And people typically prefer this expression a lot more. Now, as a result of the stress up operation, the expression we have for Q1 star looks much more symmetric. The optimal demand for good 1 is just equal to its own price raised to the power of sigma, and then divided by some kind of average between the prices of the two goods, and then multiplied by the budget. When economists talk about the CES derived demand, this form is usually what people think about. We can now substitute this expression back into equation 3 or equation 4 prime to solve for Q2 star. For here, let's just plug it into equation 3, our budget constraint. To see how the substitution goes, in our budget constraint, we have y minus p1 q1 minus p2 q2 is equal to 0. Now, once we substitute in the expression for Q1 star, what we have is we're just multiplying this expression of Q1 star by P1. So we're going to multiply P1 to this expression of P1 raised to the power of sigma over P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma times y minus P2 Q2 equal to 0. And now we can multiply P1 into the parentheses. And what's going to happen is that the expression becomes 1 minus, the bottom does not change, we're still P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma. And the top now, combining the power of P1 to the power of 1 and P1 to the power of sigma, we have P1 to the power of 1 plus sigma times y minus P2 times Q2 is equal to 0. What you will notice is that the expenditure on good 1 is simply the share of P1 relative to this some sort of average between P1 and P2 together on the denominator. And it still has this interpretation of a share of expenditure on the budget Y is being spent on good 1, but now the share is no longer just determined by a preference parameter, rho or sigma, but instead it is also controlled by how large price P1 is relative to P2. This is fundamentally different from the Cobb-Douglas utility function, and that leads to the kind of properties we'll see down the road for the CES-derived demand. Now, to solve for Q2, we can factor out the y here and the y here. So what we'll have is just 1 minus P1 to the power of 1 plus sigma over P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma times y is equal to, moving P2, Q2 to the other side of the equation, we have this. And this term in the parentheses is just P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma minus P1 to the power of 1 plus sigma over P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma. Right? And multiply by y, of course, that is equal to P2 times Q2. But now you realize that this term is exactly the same as this term, so they cancel out, and what you end up with is flipping both sides of the equation. So we have Q2 on the left-hand side. P2 Q2 is equal to P2 to the power of 1 plus sigma over P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma times y. Now dividing both sides of the equation by P2 to solve for Q2, we have Q2 star is equal to P2 to the power of 1 plus sigma divided by P2 over P1 to the power of 1 plus sigma plus P2 to the power of 1 plus sigma times y. But then, of course, this division is simply changing the power on the numerator. So what we have is P2 to the power of sigma over this weighted average between the prices again times y. And this is exactly the symmetric expression as what we have for Q1 star, with the only difference being that in the numerator we have the price for the good, P1 for Q1 star here, and P2 for Q2 star here. On the denominator, we have exactly the same expression that is, again, some sort of average between these two prices. Taking stock of the example thus far, we solved the utility maximization problem for the CES utility function and found these derived demand functions. We see that the same process of the Lagrangian approach leads us to the solution, despite of the added complexity of the utility function. Well, we can proceed from here to find the indirect utility function by plugging in these demand functions back into the CS utility function. But we will leave that to an exercise. For now, I'd like to discuss the properties of the CES demand a little bit further because they take a very important position in many economics models. You will notice that unlike the demand derived from the Cobb-Douglas utility function, the demand of good 1 is affected by the price of good 2. We will verify this in an exercise that intuitively the demand for good 1 increases when the price of good 2 increases. In other words, the consumer will substitute good 2 with good 1 when good 2 becomes more expensive. This is a much more realistic feature that makes it suitable for applications compared to the simpler Cobb-Douglas derived demand. And similar to the Cobb-Douglas derived demand, it also exhibits law of demand, where the increase in the price of the good itself would decrease the demand. These relationships are not very obvious to see immediately, but at least we're able to see that in the demand for good 1, both P1 and P2 will play a part. Because the denominator for each demand across different goods are identical in the CS-derived demand functions, and also because it can be seen at an average of prices. So sometimes people find it simpler to wrap this term up and call it a price index. This term is known as the Dixit-Stiglitz price index. So sometimes people will write some expression that indicates, let's say, P here to be this weighted average between the two prices, and then just plug this wrapped up version of price index on the denominator. We have solved the optimal demand for the CS utility function with two goods. But now, in many applications, we might want to consider scenarios where the consumer can choose among more than two goods. Well, it turns out CS utility function extends very naturally to these situations. Let's say that instead of two goods, we now have n goods, and n can be any number that is bigger than 2. 3, 4, 5, 6, 1,000, however much you want. Then the CS utility function will look something like this. So instead of summing up the quantity of two goods, each raised to the power of rho, we're just going to sum up the quantity for each and every goods, from good 1 to good n, each of them raised to the power of rho. And then at the end, we're going to raise the entire sum of all such quantities by the power of 1 over rho. And that's exactly the same as we had for two goods. It turns out that miraculously, although the utility function becomes a lot more complicated with n goods, the derived demand functions remain almost identical to the two good case. They're still just an expression of the price for the good itself raised to the power of sigma divided by the price index. The change is just that with n goods, the price index averages all of these n prices through this geometric type of mean. Well, you might have noticed that so far in the CES utility function, all the Q1, Q2 up to Qn, they all contribute to the consumer's utility at exactly the same rate. In other words, the consumer actually doesn't really have a preference towards any particular type of good. So can the consumer prefer one product over others? Well, it is always very natural to imagine in situations where the consumer might prefer pizzas over burritos, or the other way around. Well, it turns out CS utility function can be generalized very easily to incorporate this kind of features as well. In addition to having n goods, each good can also contribute to the utility function differently for the consumer. To do that, we would multiply a so-called preference shifter, alpha, for each and every good. Note that these alphas are different for every good. So that will allow us to put different weights on each good to indicate that the consumer would prefer a particular good, because having one extra unit of that good will contribute more to the utility when alpha is higher. Our previous CES utility is simply a special case of this form, with alphas equal to 1 for each good. Now, with these weights that shifts the consumer's preferences toward each goods, the demand isn't much worse either. They're still just determined by the ratio between the price of the good raised to the power sigma divided by this price index. It's just that now the price index is not only this geometric mean between all these prices, but also the prices have to be weighted by these preference shifters of alpha. But that's it. With a very small change in the price index, the CS utility function and their derived demand generalizes to offer a huge degree of freedom to model all kinds of interesting situations. On the whole, you see that the CES utility function is very versatile, while its derived demand remains relatively simple given how much feature it offers. So this is why you will likely see that the CES demand and the CES utility function appear in many different economics models. One additional feature of the CES derived demand is that there are always interior solutions. Because the prices are always strictly positive, so the demand for each good is always positive. This makes it very easy to work with in applications. It is very important for us to understand and appreciate the properties of the CS utility function and demand functions in order to understand many of its economic applications.